Hi everyone, this is Adam Hops with the National Operations Center of Excellence. Thanks for joining our webinar today on leveraging big data to improve traffic incident management. Before we get started and I turn it over to today's moderator, just a few quick notes for everybody. You'll notice below the presentation up on your screen, there's the opportunity to download the slides that are there in PDF format. Also, we've provided some links at the bottom left of your screen, including there the NCHRP project overview for this project. So feel free to go ahead and take a look there. We do mute everyone throughout the presentation, so you will be muted, but we do have an opportunity to take questions. So please use that question and discussion pod on the right-hand side of your screen throughout the presentations, all three presentations, and we'll sort through your questions and get to them at the end. So please just, as people are presenting, feel free to use that. All of the NOCO webinars are recorded, posted on our YouTube channel within a week, and distributed out via our newsletter and social media. So feel free there on the left to use links to make sure that you have access to this webinar presentation or to share with your colleagues as well. I'm going to go ahead and turn it over now to Eileen Singleton of the Baltimore Metropolitan Council to moderate this. Once again, thank you to Eileen, Kelly Pesha, Benjamin Pesha, and Grady Carrick for organizing this, and to all of our presenters. Eileen?
Great. Thank you, Adam. And I appreciate the opportunity to participate on this webinar. I was a panelist for the National Cooperative Highway Research Program project entitled Leveraging Big Data to Improve Traffic Incident Management, NCHRP 1775, and that's what we'll hear about today. I want to first thank National Operations Center of Excellence for hosting today's webinar. They do an outstanding job of advancing the state of the practice through technology transfer by hosting these webinars, and I think we all appreciate their efforts. So thank you to you, Adam, and everyone there at the center. The NCHRP 1775 project sought to tackle a topic that many of us are confronted with in transportation, the overwhelming number of data sources and amount of data in our world today. Fundamentally, we want to better understand how to access that data and harness its potential to solve real-world problems in traffic operations and specifically traffic incident management. There is an urgent need for transportation agencies to become fluent in big data technologies and to successfully integrate them within their operations so that they may benefit from existing and emerging big data data sources and tools. In today's webinar, the principal investigator for NCHRP 1775, Dr. Kelly Pesha, will familiarize us with the project and the guidelines that accompany the final report. And Ben Pesha will provide some of the technical results from the project. Following Kelly and Ben's presentation, we will share with you two real-world experiences from practitioners in Kentucky and Pennsylvania. Both of these states are doing great things with large and diverse data sets that are having positive impacts on operations in their respective states. So it is my pleasure now to introduce Dr. Kelly Pesha and Ben Pesha.
Thank you, Eileen. Good morning or good afternoon to everyone, depending on where you are. Eileen did a great job of providing a little bit of background to the project and a little bit of an overview of our presentation. So the project was quite extensive, and so we don't have time to go through everything today, but we did want to talk about what the objective was, give some big data definitions and examples, and then focus mostly on what the culmination or outcome of all the research was, and that was big data guidelines for transportation agencies. So the objective of 1775 was to develop guidelines that illuminate the concepts, opportunities, data sources, applications, analyses, options, and challenges associated with the use of big data for TIM agencies and the opportunities for advancing the state of the practice. So the report, as I said, is quite extensive, and so we do introduce big data concepts, things like the types of data stores, the types of data analytics, the opportunities for applying big data to traffic incident management and advancing the state of the practice. We do that by contrasting the more traditional approaches to collecting data and analyzing data in the TIM arena to how you would do that using big data techniques. So we make the contrast using examples from the literature. There's about 5 or 6 different examples, the data sets that were used, the analyses that were applied, and then we contrast that with, well, how would you do this from the big data approach? What data sets would you look at? What types of analytics would you apply? And then we also highlight, we looked at 31 different data sources, and we assessed their TIM-related data sources, and we assessed them using 2 different capability maturity models. One of the maturity models focused more on data readiness, and the other one focused a little bit more on data openness. So that's in the report. And then there is quite a bit of discussion about the challenges for taking all of this information, these big data approaches and all of this data, and applying it within transportation agencies. And that is really where the guidelines come in, and taking all of the information, and particularly the challenges, and making some recommendations for transportation agencies on how to ready themselves for big data and prepare and start to leverage different data sets. So what is big data? We hear a lot about the 5 V's. So what we're talking about here is extremely large data sets, and not always, but generally we're talking national scales, international data sets. I think we can all think of a few, like the probe data, Facebook. There's a lot of data that is collected at a very wide scale. Also diverse data sets. So if you have data sets that include a lot of different types of data from many different types of sources, data that exceeds the capacity of the biggest server available on the market, data that is processed using a shared resource model. In other words, the cloud. In fact, the cloud was really a result of the need for big data. It's become too cost prohibitive to build the infrastructure in-house to house this amount of data, and this variety of data. And big data is data that can be analyzed using big data technologies and methodologies. Basically, there's just so much information that different types of tools are needed versus the traditional tools that we've used in the past. So just to kind of put big data into perspective on this data size scale, while it's continuously changing, big data is generally thought to be anything in excess of a terabyte. A couple of examples: Walmart produces or processes 2.5 petabytes of data every hour, and eBay stored back in 2013 90 petabytes of data. Some of the stuff we're looking for traffic incident management includes crash data, data from TMCs, and in the near future, emerging connected vehicle data, perhaps. So as an example, 5 years of statewide crash data from Florida is less than 500 megabytes. 30.2 million records from 15,000 U.S. EMS agencies from 2015 was about 40 gigabytes of data. And data from 300 TMC field devices over an entire year produces about 635 gigabytes of data. Looking at emerging connected vehicle data estimates, we start to get into the terabyte range when we're looking at a year's worth of data. So all the BSM or PDM data from 200,000 connected vehicles produces an estimated 820 gigabytes a day, or about 300 terabytes a year. And 300 CCTVs is about 1.2 terabytes per day, or 438 terabytes a year. So that just kind of puts the data that we're talking about with traffic incident management into perspective for some of these big national or international data sets. So the move from traditional data analysis to big data analysis. So traditionally, data is pre-processed using an ETL, extract, transfer, load process to fit into a relational database schema. And then it's analyzed using statistical software and business intelligence software. Now the data is becoming too big, too diverse, and too messy for these traditional tools to work well. So big data, on the other hand, rather than put through an ETL, which transforms the data and fits it to this restrictive schema, it's stored as is. And then the big data tools have been specifically developed to process these big data sets, and they don't work particularly well on smaller data sets because they're really designed for big data. Big data is a rapidly and continuously evolving ecosystem. The tools are changing very quickly. The architectures are changing very quickly. And I think, one of the most important things is that this move from traditional to big data is very disruptive, and it requires a complete paradigm shift in the way we think about collecting data, storing data, processing data, analyzing data, and even using the data for decision making. So just as a little bit more compare and contrast, and again in the report we take actual studies from the literature, traditional approach studies, and we compare them for how you would apply a big data approach. But basically the traditional approach is somewhat slow moving. It's based on samples of data, limited observations. Oftentimes qualitative approaches are used, which can be subjective. Often some of the approaches are manual, tedious, and resource intensive, which leads you to do the study once and then not usually repeat it because it's just too costly to repeat the study over and over again. So you take the study results from the one study or the one study every 5 years or 10 years and you apply the results widely. And that's because you capture the data, you run the analysis, and then you apply those results to change some standard procedures, and this is done fairly infrequently. On the other hand, the big data approach is much more fast-moving. It's based on large, expansive sources of data. There's many opportunities to explore and analyze the data because you can run tens of thousands of variations of analyses very, very quickly. It doesn't take a lot of time. It helps to reduce the subjectivity of analysis because you're working with so much data and such a variety of data, and you can repeat the analysis. If you set it up once, you can repeat it over and over again as new data is available. It's much more easy to do that than the traditional way, and it's designed to be actionable right away. So what are the opportunities for big data and TIM, or transportation agencies? And really, the results, or the opportunities are kind of endless. It could be used to gain efficiencies, develop or evaluate policies, improve resource management, improve safety, enable predictive TIM. But to get to the point where this can be applied and these benefits can be realized, there are a lot of challenges that need to be overcome. And we won't really go a lot into these. They're listed here on this slide. But they are detailed in the report, and the guidelines really do speak to how to overcome a lot of these challenges and what are the steps that need to be taken to break down the barriers for transportation agencies to begin positioning themselves to leverage big data. So I'm going to turn it over to Ben to go through a high-level summary of the guidelines that are in the report.
Thank you, Kelly. So these are pretty much a very high level. There's 8 categories. First one being to adopt a deeper and broader perspective on the use of data. Once we collect a lot more data or acquire it. Third one is to open and share the data. That's also an option. And then common data storage, adopt cloud technology.
Hey Ben, this is Adam. Do you mind pointing your mic? Your mic is really low.
Oh, let me see if I can.
Sorry everyone, we'll get it fixed here real quick. Ben, it looks like you're now muted.
How about now? Is it better?
Yes, that's a little bit better. A little louder would be great.
Do you want me to? I have it at the microphone volume. Do you want me to call in, or do you want me to try to keep on going that way? I will try to hold the microphone close to my mouth.
This is perfect. This is much better. It's
Okay.
perfect.
So these were the 8 guidelines that we talked about, and the last 3 were manage data differently, processing data, which is also different, opening and sharing the outcomes. So adopt a deeper and broader perspective, and pretty much big data is really beneficial if it's approached in a collaborative environment. There's just too much data for a limited few sets of people to look at it. It has to be open to a lot of people. In order to do this, there's really needs to be a trust in the decision making that's driven by data analysis, looking at data, monitoring. Often what we see in agencies is a people and process approach that's reactive decision making based on intuition, personal opinions, business experience, business understanding, that is often there to compensate the lack of data in work. A shift towards relying more on the data to make these decisions. Expanding the decision beyond a chosen few, it is, and often this is what came out of the business intelligence days, is that a lot of the data analysis was done for a few to make the decisions and cascade down. In a big data setting, you will want to have even the lowest level of the organization capable of looking at the data and make decisions to them. Given the infrequent nature of the traffic incidents and the shared, it may be also useful to share just beyond an organization, but across every organization nationwide, in order to have a lot more data to look at than just the ones that you have in your own state organization. Collect more data. We hear that very, very often, and everybody is focused on software and tools and how they can acquire software and tools to do big data analysis. But really what primes, what is very important, is to collect more data. There is not enough data being collected. The focus is more difficult because there's a lot of challenges in being able to collect more data, especially if it's currently based on human collections, equipment, a legal hurdle. But it is, the more detailed and the more extensive the data is, the better, the more insight you will get. Without enough detailed data, it will be very difficult to be relevant. The other thing about collecting the data, which is often misunderstood, is that some data is worth collecting. Some data may not be worth collecting, but may be worth using third parties to increase that data. Here's an example of it. If you were to collect information about a weather conditions or road weather conditions, incidents, you could ask someone to record it at the same time that they're filling a crash report. Or you could have very reliable location and timestamp, and then tap into many of the weather services that will give you, hundreds of different variables for weather at that location at that specific time. That way you can enrich your data without necessarily collecting it yourself, but relying on the collection that people dedicated to that specific data can provide you. NOAA has a lot of things. Readily open and share the data. This is something that is really important, because the more you look into the big data, the more you realize that what we call ancillary data sets can help a lot in the analysis of things that you want to do. For example, coordinating traffic data with incident management to have more queue information, flow of things. And what we've observed in a lot of the organizations that we looked at is that there are common roadblocks to data sharing. The public record laws, the proprietary data formats from one organization. Or sometimes the contract data clauses, like see with your ways and INRICS, where you can purchase the data, but you're very limited to what we do with it. So there is a benefit in trying to adopt a an open data, which is like allowing the availability and access, the reuse and redistribution, and allowing universal participation. The use of a common data storage environment. It is very common in every organization to find data stored in different relational database file storage, so things like SharePoint, find like all over the organization, and usually are funded by different groups. But when you're dealing with big data, the size of the data sets is such that you cannot just put it into one area. You have to pretty much avoid trying to move the data from where it's located and managed to where it needs analysis needs to be brought to the data. And in order to do this, the best way to do this is to use a common data storage environment. The reason is because, and this goes back to the cloud argument that Kelly was making before, is that these data sets are usually so big that you cannot store them in just one single server. You have to have a server cluster, a group of servers with some kind of reliabilities and redundancy built in and store that data efficiently. The other thing is that duplicating these data set may be very cost prohibitive if you have to copy the data from one server that stores and manages like it is the traditional way. Now, there are a lot of talks and products that have been coming in about something called data virtualization. Data virtualization is a virtual view of a unique data store on top of all your distributed data sets. While these are starting, and they're starting to be promising, their analytical capabilities are still very limited at this point, and outside of simple aggregation, simple queries, it is very difficult to run much more complicated analysis on this data virtualization. So this is something that needs to be maybe valid in the future, but at the moment, a really common data environment is needed. The adoption of cloud technology for storage and retrieval of the data. The cloud, just like Kelly said, has been created pretty much out of the need to handle big data. And I need to be able to have reliable hardware, because at that scale, pretty much server will fail very, very often when you have very, very large data to store. But it does bring economies of scale by allowing your institution to share the cost of IT infrastructure with others. And it is often a problem for security reasons or very reasons about this. It's still like a work in progress in the adoptions. But it brings agility, scalability, and affordability to store the data. And it's also usually very secure. I've seen many organizations that had been had cybersecurity issues, and the only part where the cloud, where their cloud was the only part that wasn't attacked because it was too secure for it. But they've made a lot of progress in securing this, even for governments. The other thing is, and I think this is the most important point, is that the cloud is usually providing services for analytics, or software for analytics, that are on a pay-as-you-go basis. And in this case, you don't get tied to specific software. But if over the course of time new data comes in, or new visions on how to handle the data comes in, you don't have to get stuck with the current software you're using, SAS or Oracle, and already paid license for so long. But you can switch from one type of analysis to another one that question. And that analysis, the cloud will allow you to stack up a cluster of tens of thousands of servers to look at one big data set within a few days, and then have the results of your analysis. Then in a few days do an analysis with another set of servers as big, different software. All you will have this ability to have a very flexible and pay-as-you-go infrastructure. The management of the data. Typically, the more when we talk about data management, they're very, very much tied to the systems that they're in, especially kind of enforcing what are the tools that need to be used to process the data, and how the data should be stored, and what kind of format, and the written relates to relational database algorithms. In big data, like we said, the data is stored as is, and it has to be fairly accessible and open and shared, increase the values of access. So the focus now is on how to create a very uniform layer of data that has a lot of quality settings, quality metrics associated with it, but that is easily usable by anybody that wants to. So it could be the structure of the data, using flat files or files that are like not too hierarchical, so the data can be accessed. Or it could be the use of open standards, use locations, typical lat-long or geohashing are being used in big data analysis, rather than outposts or location systems, DOTs. You have to ensure that every single one of your records is uniquely identifiable. Compared to relational database, this is not difficult, not necessarily managed within the data set, within itself, because it's just files that are being processed. So you have to define within your data some ways to uniquely identify. You have to manage access to the data pretty closely. And usually it's done by the file level, by allowing access to specific folders or specific files in order to have this, rather than they have a system that is able to allow for control of privacy. You pretty much create the other thing is to protect the data without locking it down, and this has more to do with like the use of PII, which is a big question in domain. The issue here is to try to obfuscate or encrypt the data in such fashion that not so much can be revealed about the data, rather than removing it altogether, because once the data is removed, there's no value for it now. So I would suggest that some of the techniques that are currently being used by NIST, that have been developed by NIST, in obfuscating genetic data, talked about that. Process the data differently. The processing of the data, we process the data where it's located. It is often recommended to use open source softwares or cloud service software that you have as you go, are very low cost. You can have very large spikes of data analysis. You don't want to have to pay software for an entire year license. And do not reinvent the wheel. Big data has been around for almost 10 years now. There's a lot of tools. 6 months. Find the one that works. Find another one if you want, but you are susceptible to find no one. And the last point would be understand the ephemeral nature of big data analysis. It is not necessarily the fact that the first analysis that you're going to develop on a data infrastructure will remain the same for several months. It is very, very likely to change within a few weeks or a few months as you fine-tune it, as you rebuild it, as you optimize it, as you discover new software and find as you go. Very, very fast process where analytics change. They're actually big data analysis, software development cycles. Private sector. And then the last is don't keep it for yourself. Whatever you're able to do with big data analysis can benefit others. So from government to contractors, universities to private sectors, there needs to be a way to maximize the values of those big data sets that, like I mentioned at the beginning, are very complex to look at. And if you need to verify the analysis that you have, if you patterns, visualization, discovery of outliers in that data raises questions. It would be very useful to share those outcomes, share those knowledge, discoveries with others, get to the bottom of it faster, and being able to optimize. I think that's the last one.
Okay, great. Thank you, Kelly and Ben. And before we move to the next speaker, I just want to mention that as they noted, one of the central findings of the study is that in order to leverage the most benefits of big data, we should look at TIM data for a large geographic area, such as for multiple states or even nationwide, as Ben noted. And another notable finding is the need to manage and process big data differently, and to change technical, organizational, cultural, and institutional capabilities and approaches to truly benefit from big data. And that is why the 1775 panel has submitted a follow-on project for consideration for NCHRP funding. And I believe the project, called Experimental Implementation of Big Data Analytics for Traffic Incident Management, will be one of the projects on the proposed NCHRP project list that will be voted on in April of 2019. So if this is something that is of interest and that you are supportive of, anyone from state DOTs can talk to the folks that vote on these projects and encourage them to select this one so we can continue the progress that we're making with TIM and big data. And with that, I want to introduce our next presenter, Mr. Chris Lambert from the Kentucky Transportation Cabinet, where he is a systems consultant. Chris, please take a few minutes to tell us what you're doing with big data in Kentucky.
Yeah, thank you so much. Can you hear me okay?
Yes, great.
Okay, great. We'll go ahead and jump in the presentation, but yeah, I'm a system consultant for ITS, and got into this a few years ago. Everything kind of came together at once. We had some record cost on storms, and then we also had Waze put out a call asking people to join in with their partnership, and just everything kind of came together, and we really needed an entirely new way of thinking and a new platform, new tools, the whole thing. So that's kind of what led to this big data project. So I'll go ahead and get started. Current and future use cases, we're currently, we use our big data system to comply with our real-time management system, our ITS federal requirements. I think everybody kind of, the first thing they want to do with real-time data or big data is kind of situational awareness, and posting everything to maps and things, and just kind of understanding everything going on. And then we also had a kind of a really cool little incident detection script that ran. Once you'll see that once you start putting this data together, it becomes very easy to do analytics, and especially with us doing, we process all of our data in real time, so now we can do real-time analytics and find crashes and incidents that happen on our roadway that we otherwise would not know about. And then we needed a way to get our costs under control for snow and ice, so we're using this for fleet management and material management for snow and ice operations. And then we really wanted to also, of course, part of the point of our presentation here is for traffic incident management. We really wanted to start detecting, not only detecting incidents, but also seeing, how long things were lasting on the roadway, see if we could detect some of the performance measures in the TIMS program, secondary crash detection, etc. So, and then the stuff over on the right side, you'll see, those are future use cases. Those are things that we're working on now that we're studying. But yeah, our big data system's kind of taken over the cabinet, really. It's kind of fun. So, so getting started, like I mentioned, we started this in 2014. And I like to tell everybody we're a great use case for big data because we've made all the mistakes that you don't have to make. We have, I don't know, gosh, probably 3 or 4 different versions of our data over the last 4 years, just because we keep finding new things. And I'll get into some of that later, but there's always something you miss. And so, yeah, we're a great use case for that. But, this our management, the one thing I had kind of going for me was the record cost on winter operations. So there was a financial incentive there to do something different. Management, we had some younger and newer folks in management, and they wanted to do something different. Everybody's always trying to do more with less. Big data can allow you to do that. And then, I think everybody talks about, it's very cliche, but I think everybody talks about the silos. And so the one really interesting thing we do is we dump everything into a common data store and then it's just very open. We allow people to kind of go in and experiment with those different data sources, kind of like what Ben was alluding to with being very open and transparent with all of the data. And then meet users where they are. That's kind of a motto or a mantra we've taken up. All of our data is harmonized based on location and time, and so we add somewhere between 35 and 45 fields of metadata to each and every record that we receive, so that our engineering staff and others can not only start looking at new tools and new ways of analyzing data, but they can also use their traditional tools. We really wanted to kind of bridge that gap in between the old and the new. So we add all of that information in there because that's what they're accustomed to using. And I'll get into some more of that. So some of the challenges that we faced from an IT standpoint, we've got a centralized IT architecture, which is not the most efficient way to do things. It may be great for purchasing, but when you need a cluster of servers and they don't understand the technology, they don't understand the use case, and it becomes very difficult. So we requested 21 servers when this thing got started, and we ended up with 7. So we had to make do, which is another reason we've gone through so many iterations, not only of our platform, but also of our data. We also were using non-standard languages. Typically, we're a Microsoft shop. Everything's done in C#, and they use SQL database, SQL or Microsoft SQL SQL database or Oracle. Sorry, keep tripping up there. So very traditional organization until this came along. And this is all very different. This is all open source, Java, Scala, Python. Our IT department they weren't big fans, especially of Python and Scala. Those were considered quote-unquote scripting languages and not, real languages. So they were very skeptical of that. So a couple things we also learned, and it looks kind of tacky on the screen, but I put it there for a reason. These big red points is always store the raw data. As Ben also mentioned, having a data lake concept where you store that raw, unprocessed data, that's extremely important. We ran into several issues where our department said, well, we don't need to do that. We don't need to store raw data. We're parsing it and processing it for you. And ran into a situation where the developer did not understand why we would want data that was not on a state route. So he just decided to purge that data for me. And obviously I wasn't very happy about that. But so he decided on his own what data we did and did not want. And we had no way of going back and correcting that because at the time we were not storing raw data. So we've learned that lesson. Always, always, always store raw data. I cannot say that enough. And also the timestamp. You think you know when something is happening or when something happened until you have to figure out when it actually happened. Several of our data feeds have multiple timestamps, so trying to decide when something actually happened or when something actually existed on the roadway is kind of interesting. We actually, and I'll get into this as well, we add several timestamp fields to each and every record that we receive. And so time has actually been much more difficult to understand than what we thought. So take some time when you try to figure out time stamping. And then also we match all of our data up to our linear referencing system, which means that we have to continuously update historic data as well. So every time our LRS is updated, which is actually every week, we have to figure out what changed and then reprocess data based on that change. Now I will admit, we have not actually started that reprocessing as a normal part of our business yet, but we're still trying to figure that out. but that's something that has to happen. You have to keep reprocessing data in order to go back and review that historic data and come up with those trends. And then location. Location obviously is very, very important. A couple of our GIS guys are involved in our big data project, so they're always talking about location. So we do several things with that as well. I think if I knew if I knew then what I know now, I think I would have had someone else involved. I had other people manage this thing. Business customer challenges. The debate over authoritative data seems to be ongoing. When you start with us, it was not only did we start aggregating probe data, we also looked at crowdsourcing data and multiple crowdsourcing data. Not like Coco Raws has precipitation data that's crowdsourced. Waze has traffic data that's crowdsourced. We were looking around for any free data source that we could to put together. And so then the issue becomes what's authoritative. You know, that data didn't come from us, can't be verified, it wasn't collected the way we collect data, and this debate starts about, you know, is this authoritative or not? And we're still working through that. I mean, I think the data speaks for itself at this point. We're 4 years in, we've got a lot of use cases and a lot of proof that this stuff works. And then just, you know, overall doubting of the data. When you're looking at detecting 38 incidents on your roadway, but your traffic management center only hears about 10 of them, they doubt, or they want to doubt, the data that you're seeing. And then just the overall resentment and lack of control. When you're starting to process data automatically and push this into dashboards and maps and things, not being able to manipulate that data before it's published is also kind of a sore point. And then just generally just fear of unknown. You know, it's new technology, it's a new way of doing things, completely different way of thinking, and that was not just from the customer side but the IT side as well, and then just overall resistance to change. We've dealt with all this, I mean, and we're still dealing with it 4 years into it. So what kind of data am I talking about? We get probe data from here, we get Waze incident reports, we get icon speeds data, if you've heard of them. We've got a lot of different data sources, and we put all these together. We harmonize all of these based on location and time. As I was mentioning before, we've got Twitter. Twitter can actually be very interesting. You can, we actually have 3 different snapping algorithms for Twitter, so we can snap to a large geographic area like a district, we can snap to a county, or we can actually snap to a mile point on the roadway, which is really fun. So what do we do? What kind of architecture are we using to do this? We use the Apache stack, or mostly the Apache stack. We use Kafka for our aggregation. We're using Spark to process that data. And by processing, what I'm talking about there is matching it up to our linear referencing system, so you get a district, county, route, mile point, etc. And then we use Elasticsearch for that, you know, kind of your hot storage, your big data indexing, dashboarding, reporting, all that great stuff. And then Hadoop really is more just for code warm storage, you know, just kind of historic stuff, but it's also processed. And then we also use Hadoop HDFS for our data lake as well. So our unprocessed stuff goes into Hadoop, and then a version of our processed stuff goes into Hadoop as well, and then Elasticsearch. And then some of the stuff that we want to put out for situational awareness and dashboarding, we push up to ArcGIS Online from Elasticsearch. So that's kind of our overall workflow. In this slide, I just kind of threw this in there just to let you know that, you know, we're using the cloud data distribution of those open source products. So we use them for service contract, Elastic, and then Esri. So why do we choose this? I won't read the slide to you, but this is basically our performance difference here. The really big part is the Spark, the harmonization processing. It used to take, on Oracle, it used to take about an hour per 1 million records, and now we're doing about 6 million records in less than 5 minutes. So as we're getting data in, you're only talking about 200-300 records at a time from any given data source. You're looking at, you know, like 23 milliseconds or something for processing. It's really It's really pretty fun. And then visualization and mapping it too. Kibana is great for aggregating a lot of data to map for heat mapping. So these are some of our added fields. You can see there timestamp. We actually have 12 different fields for timestamping. That's how important it is. We actually have more fields for timestamping than what we do for location data, for tabular location like district, county, and route. And then we've got 6 for geometry. The snapping, part of our process is to calculate a probability on that record to see what the probability is that it snaps to maybe a ramp versus a bridge versus the interstate, for example, and then it snaps to the most probable. So anyway, so we store all that as well. And then route-specific information like classification, ADT, etc. And all that allows you to, after the fact, after all that's processed, creating derivatives or reports or dashboards and things become very, very easy at that point. So just to give you some context here as to what kind of data we're talking about, we pull in about 4 terabytes of data per year of just raw data. And then after you're processing that, we've got 6 terabytes of processed data in Hadoop and 6 terabytes in Elastic. So, altogether you're looking at somewhere between 16 and 20 terabytes of data. Those are fairly conservative numbers. So that's kind of the size of the data you're looking at for us anyway. Now, if we were to equip on a DSRC in the future data, if we were to equip all 2,500 of our signals or our controller cabinets out in the field with DSRC, then you're suddenly looking at these numbers just for a single data feed. You're suddenly looking at 768 terabytes of data just for a single data feed on top of what you're already pulling in for your other data feeds like traffic and crowdsourcing, etc. So you're looking at close to a petabyte of data per year just for a state DOT, which is really kind of unheard of. The future, our platform allows for 3 different types of machine learning. With that much data, we're really wanting to apply machine learning just so Tableau is not going to cut it at some point. So we're going to have to start looking at other ways of processing this data, not just processing, but just trying to understand the data. And so we've got 3 different types of machine learning we're going to try to apply to our data for different use cases. And then also just basic visualization. We've got dashboards and we've got maps, but at some point the data is going to become so overwhelming that you're going to have to look at maybe 3-dimensional modeling of data, and we're starting to kind of experiment with that. And then what kind of derivatives or apps or derivatives? Once you have, your data almost becomes part of your architecture at this point, and or part of your computer architecture. So after the data is organized, suddenly it becomes very, very easy to say, oh, okay, yeah, we can make a real-time map to replace our 511 system. That's not a problem. So we did that. We produced GoKY, and we just push up some of the data from our data store to ArcGIS Online, and that was our 511 replacement. So that saves $750,000 per year, and it allows like Kentucky Emergency Management, Kentucky State Police, other agencies actually use GoKY for their dashboard, like a real-time situational awareness dashboard. So it may not serve the public in the best manner. It's kind of cluttered, I guess. It's got a lot of layers of data on it, but it saves us money, and it allows our partners better understanding of our activity across the state. Incident detection, here's some of the stuff that we picked up there. With that little script, we actually compare traffic data with Waze reports. So when crowdsourcing reports come in of an accident on our roadway, we then check the speed, and if the speed is depressed, we then send out an email alert to some people, or the reverse. If we get a drop in speed, and we also then go look for a crash report from Waze, when those 2 things match up, again, we send it out. So very easy to do once you actually have your data organized and processing in real time. After action review dashboards, these also become very easy. You see the middle or the top part there, we actually have crowdsourcing reports in different categories, people reporting traffic jams, etc. So we can see when those start, when they end. We can see how many people, based on the color, We can see how many other reports we have in that same area in that same time frame. And then in the middle of that, we've got graphed speeds so that we can kind of visually see the correlation between crowdsourcing reports and our probe data. And at the bottom, we've got our TOC data. When did the call actually come into our call center? And then for snow and ice, we've got decision support systems, kind of the same thing, dashboard, situational awareness. Again, all these become very easy once you have your data organized. This is actually, what we've got here is we're actually graphing air temperatures along with speeds, along with our snow and ice activity, so that we can possibly reduce the amount of salt that we use during an event. So if the temperatures are trending upwards and the traffic speeds are trending upwards, that allows us to go ahead and make the decision to stop using material and maybe continue plowing, save a little money. This is work zone monitoring. This is another kind of dashboard that we threw together. So again, all these use cases throughout the cabinet really apply to different areas of the cabinet, but we're all able to use, we're all using the same data for different, what you would normally consider a standalone app that people would be looking for or getting data to populate. Another work zone monitoring app, this is using the icons data along with Waze. And this actually matches up with our LRS. We can actually see the mile points, the speeds at the different mile points. So not only are we able to see and graph the speeds per 2 minutes, we're also looking at the individual mile points and speeds at those points. So you can actually see where the crash occurred. You can actually watch your queue kind of line up or pile up, if you will. And then everybody wants to know, how many people do I have doing this? We only have a couple. We've got 2 developers, we've got a GIS guy, and myself. So this is actually a very small team that managed to do this, and we continuously work on this project. The GIS guy is about 50%, the other 2 are full-time, and we still have probably another year's worth of work queued up for those developers. And then this is the reality check. This is why that we do what we do. And especially talking about traffic incident management, the data actually showed up. This person, this is a fatality on our roadway that happened at 10:30, and we started seeing data on that fatality at 8:39. And so that was 2 hours, just a little more, a little less than 2 hours before the fatality occurred. Now, not to say that we could have done anything different, but in the future, I would like to say that, yes, we can do something different. We can prevent these. It's just, it kind of puts things into perspective when you have data 2 hours before the fatality. And then I'll take any questions. I guess we're seeing that at the end or something. So anyway, there's my contact information. All this is available on the slide. And I will turn this over now, I guess, to Pennsylvania Turnpike, I think, is going to speak next, and I will mute myself. Thank you all so much for listening, and I appreciate it. And please give me an email, or send me an email, or a phone call or something, and I'll be glad to help you out. Thanks.
Great. Thanks a lot, Chris. And while the Pennsylvania folks get ready, I'll just do a quick introduction. We have 3 presenters from Pennsylvania Turnpike to show us how traffic incident management has been improved with the acquisition and use of unique data in their state. Todd Leiss is the TIM coordinator for the Pennsylvania Turnpike, John Parker, the Traffic Operations Project Manager, and David Ward, the SAP Business Intelligence Supervisor. So, gentlemen, I'll turn it over to you.
Good afternoon, everyone. This is John Parker. I'm a Traffic Operations Manager here at the Turnpike. Dave will be assisting me on the presentation. Again, we're not probably as fancy as what Kentucky's doing, but we'd like to get there. So we are in the beginning stages of big data and what we're doing for our TIM timeline. So how we collect the data, and we're kind of unique on how we collect the data and what our dispatch center does. We actually have a TOC, or Traffic Operations Center, that actually dispatches a lot of our emergency response for traffic. So when we dispatch, we actually have contracted fire, EMS, and towers, just to give you a kind of frame of mind of how we do things and what kind of roadway we're monitoring. There's 550 miles of roadway that we monitor. So we actually dispatch maintenance, fire, our EMS, and our state police. We have our own state police for all the data that we're collecting for the TIMS timeline. So basically, it's a computer-aided system. It's CADs. A lot of people have CADs, or the county 911 centers have CADs. So that's our computer-aided dispatch that's in our operations center. Again, it's just preloaded software. It's an Intergraph hexagon software that we use now to gather a lot of the information. And just that little small piece of information is good, but we have a lot of different other third-party information that's coming in, like Waze and Twitter and Interx and a lot of different third parties that we're starting to build this big data picture. So if you are along our highway and you call star 11, it comes directly to our operations center, and that's how all the data starts coming in. So the big data flat facts, I just want to give you what we collect and how we're collecting, and I'll let Dave talk a little bit about how much data we're getting.
Hey, we're not quite to the large size, terabyte, petabyte size yet, but so we collect our INRIX data, and we store that at every 5 minutes. We'll store INRIX data. Same thing with Waze. Our NOAA one, we're just starting now to store our weather data every hour. So as you can see there, our numbers aren't real huge on what you might call big data, but we're slowly getting there. Eventually, we'll be storing connected vehicle data, some other roadway type sensor data. So like John had said, we're just in the beginning stages.
So I guess a lot of our data challenges is linking to a common data set. We do geospatial, and a lot of it is location, a lot of it is time, just like Kentucky said. And to start building that big data, like Chris said in Kentucky, we're doing it down to location, we're doing it down to time, but we're adding so much more to it. We're adding the weather and the Waze data and the Interx data and all kinds of different stuff to it. So it's just starting to build that data lake, and it's kind of a scary proposition that we can start collecting our crash data into it, our tracks data, which is our state police crash reporting into it, and trying to correlate and link all that stuff together it's a pretty big challenge. And the other challenge is the Waze. Our Waze incidents to our actual accidents. Like, okay, when somebody's going down the road, they're reporting a Waze. How far were they away from that accident? Were they before the accident? Were they a half mile before the accident, a half mile after the accident? Did they report it 5 minutes before? Or are they stuck in the queue that they're reporting the accident? There's a lot of different correlations that you have to look at when you start getting this data in. It's great data to have, but that correlation for Waze back to your incident that you actually want to relate it to is not the easiest thing in the world. So that's one of the challenges we've had combining and linking some of those data sets. So the data we store, we went over. We store Waze data every 5 minutes, Dave?
Yes. Yep.
Yeah. And then the CADS data we store, that's real
time.
That's real time. And the Interx data is every 5 minutes.
Oh, so, yeah.
So we're getting a lot of data. A lot of data is coming in. Again, weather, he just said about an hour. But so we have all this data coming in, and linking it all together is pretty big challenge. So how long an interval, I guess, IT is basically saying, this is when we can store it and how we can store it and how much we can store. So we're looking to get that information in, and it be quantitative to us, to the fact of how granular do I really need it? Do I need it every minute? Do I need it every 2 minutes? Can I survive with weather every hour? So that's like some of the questions we're always challenged with when we look at this big data stuff and look at collecting this data. So I think a lot of when we started getting into this with our CADS data and the TIMS data that comes in, it's very challenging because we have so many operators and so many duty officers putting stuff into our databases to, I guess, make it foolproof, make it as foolproof as possible, that people can't just put something in an open text field. So, we want to improve our data collection, and I think the only way we could do it is we have to train our operators more to put the right data in, and we actually have to come up with quality control processes to help us get the better data. And we'll tell you in our TIM timeline, it's not 100% foolproof. Some of the data in there is not good data. So we've noticed, bringing all this data in, we've also noticed, hey, we've got a lot of front-end work to do on it. And I will tell you, that's probably the most important thing. You can build the biggest lake you have, but it all depends on what somebody's throwing in it. So, and what they're throwing in it. So you could just be careful with that, and that's kind of a lessons learned we have. The architecture, I'm going to let Dave go over how we actually build it and what we're bringing in.
So this kind of shows you that we try to get it down to the lowest level of detail. I know Chris mentioned before about storing the raw data. This is kind of illustrates that also, that everything on the Turnpike really comes down to a milepost. I mean, to be specific, the milepost and direction. So we always try to get, if we have that long, we can get to the nearest milepost, which is a tenth of a mile. And of course, date is also an important one. So we always try to link everything together to at least the lowest common as possible. And from then we can start pulling in other data within our system, such as our CAD system, like John mentioned, Waze, our maintenance data, HR, our tolling data, and we start linking that data together and from there we might find other things. Where the deer strike, why are deer hits more prevalent here or there? Somewhat of the fundamentals of starting to get into some AI and some predictive analytics once we can start linking all this data together. And then from there, we might start learning of connections that we never even thought of to look at. So the main point is try to find that lowest common denominator to link the data together.
So I guess one of the biggest challenges is the TIM timeline, and I'm just going to go into the TIM timeline because I guess this is what we're trying to get to, is to come up with those definitions of what the TIM timeline is. FHWA has their definitions, and they're great definitions, and we try to get as close as possibly we can to them. But based on the data we have and how we collect it, we really had to come up with our own definitions to make sure that we have the correct timeline and we're measuring the right things. So I know you can't see this, but you can download it, and this is what we kind of came up with as far as what we're pulling from CADs, what we're pulling from our track system, and we're trying to get the best timeline out that we possibly can. And again, we got to refine a lot of this stuff because we're noticing, if we're building this timeline, that hey, we're not really to the definition we want to. We're not really to the data quality that we want to get to. So I wanted to kind of stick it in here. Before you go into the metrics, the data that's coming into it, how you define data, and minus this, divide this, and what the percent is. And I just want to make sure that that definition of the timeline that everybody's coming up with or trying to come up with, you guys really look into your data and come up with the best possible definition that you can have. So just to give you an idea of how we came up with the TIM timeline and what we're kind of using, again, Waze, the Interx, the AccuWeather data, and our CADS data, these are all in different places. We want to see it, and we wanted to see it somehow in a dashboard and start defining that timeline with the data that we have. So that was kind of the business need of kind of building the TIM timeline or IM dashboard that we have. So the dashboards, it's probably easy to build, it's easy to train. If you put a dashboard in front of somebody, it's kind of self-learning. So we wanted to make it as easy as possible, and I'm going to show you a sample of what the dashboard looks like. But it's easy to drill down. You get the whole picture. You can drill down and get whatever picture you want to paint, you can get. So we really wanted to focus on getting this data into the dashboards. So we have two different dashboards now. We have authorized service providers, which is our towers. We wanted to see how well they're doing because they are contracted to us. We pay them for every tow. And the other one is the TIM timeline. I'm not going to go into a live demo. I'm just going to really show you some screenshots that I have of the TIM timeline and the authorized service provider timeline. Because again, we have to measure our authorized service providers, our towers, on some sort of timeline. And then we have to measure ourselves on how good we're doing, how we're dispatching, how we're getting the roadway cleared as soon as we possibly can. So I'm going to go to the next slide. This is our traffic incident management timeline. As you can see, you go through the timeline of when we actually activated or when the first responder got there, when the roadway was cleared, the incident timeline, when traffic was back to normal, and then again, we're using Interx for that because if it goes above 60%, we want to make sure the traffic's almost back to speed. So it gives us a good idea of what's going on with our timeline. And again, if you look at it here, we have it by current fiscal year and previous fiscal year to see if we're actually doing, how good we're doing, based on from one year to the next. Just to give you an idea of the filters, you can do day of week, you can do type of incident. We can do anomalies like over 36-hour incident that was over 3 days, or incident that was under 3 days, or an incident that was under 12 hours, under 2 hours, the type of incident, whether it was incident of accidents, accident blocking, the type of vehicle, whether it's commercial or passenger, the type of weather condition. If you just wanted to see icy incidents or snow incidents, we're relating all that back to big data because in our, we just started storing our weather information, but we had a little bit of a weather thing in our crash data in our track system. So we had to do that correlation between our CADS data and our tracks crash data for state police to get the weather condition that happened at that incident. We could do it by different responders or how many fatalities we had. And then you could do it just geographically by location. So by date, by weather, just going down through there. So just to give you a blow up of what it actually looks like, because you can't really see it on the screen. You'll see Interx there. You'll see Waze. This year we've been getting Waze incidents about 2 minutes before an incident has come in. Again, that correlation between the Waze and the accident, it's pretty hard to do, and we're trying to do the best we can. So, but this is what the incidents look like and what the incidents look like as a whole. I will tell you, a lot of these incidents we may not have roadway clearance for, or an incident clearance time for. So we have to filter through all of this data to see what's valid and invalid. Are our operators putting in the right data? So again, it's a great tool. It's great to look at, but we have to make sure that the data we're putting in here is right. So again, gives you Waze timeline, first responder, roadway clearance, incident time, and then the Interx speed back to normal. So gives you a little bit of a snapshot there. What I like about this is any information that we filter on, I have an Excel spreadsheet I can go to, and if you look at the third column to your left, there's an incident number. That actually goes back into our CAD system so you can get details of every single incident that you're looking at. So if you have a problem and you want to look at it, you can just look, you can click on it and it actually links back to our internal system so you can get more information. Again, you can export to as Excel, you can look at CADS data, you can look at the link. So here's what our CADS data looks like. Again, this is like the details of the incident, who showed up, when they got dispatched, when the incident was actually cleared. So it gives us a pretty good link. So this is our roadway clearance time. And again, we can do this by type or subtype or fatal or the type of incident or type of weather or type of time. You could do it a couple different ways. So it gives us a good idea of what's in traffic conditions back to normal. What's our time in what we're looking at for a fire. It's 48 minutes. So maybe we look at fire, and then hazmat, it doesn't take that long to get traffic back to normal. So it's just little kind of things we run through here. It shows us our incidents, but again, we wouldn't have any of this data if we didn't start linking it together and thinking about big data. So here's our authorized service providers. Again, this is just acknowledgement time, arrival time, departure time. They have to be under 15 minutes for them to respond, and 45 minutes upon arrival, and they have to depart within a certain time, so it gives us a good tool to go back to them and say, this is how you're performing. And again, the filters and the gauges per the measurements, we could do any type of authorized service provider there. So that gives Todd a good gauge on how everybody's doing. And again, by district, by incident type, by provider, by weather. If there was an entrapment, how long did it take them? And again, I want to go back down to, you see that data flag, valid versus invalid? We're going through that now to see what we can do better. And this is just our number of events and number of towers. As you can see, Rob's Automotive, they're down by Philadelphia. They have the most. So, you know, and what their actual times look like and number of events. Pretty good gauge on, you know, if you're going to contract towing or look at your towers. And how good is the actual operator as far as response times. I'm just going to go through here and we're just filtering out some anomalies we may have. But it just gives us a good idea of what's going on. This is insufficient funds. We do have people that don't have the funds to be towed off the Turnpike that we actually pay for, and then we ask for reimbursement. And our management wants to know how much money we're actually spending and when for insufficient funds. So that's really basically it. Again, you can sort it to Excel, you can add it to a spreadsheet, you can sort the data. Gives us kind of a one-stop shop. And that's basically it. That's all I have. Again, some pitfalls we've had, I think we went over in bringing all this data. And again, we're in the infancy stages of building a data lake and correlating all the data together. I will say that a lot of the third-party stuff is good to have, and to get down to the raw data is great to have, because then you can get down to that granular level that you may want to get to. So that's it. Thank you.
Great. Thanks so much, Todd, John, and David. And it sounds like you're doing a lot of great stuff with the Pennsylvania Turnpike, and it was interesting to hear all that you're working on. So there's been a lot of activity in the chat pod, and some of the questions have been answered, but I think we'll try and go through and hit them verbally, so people, if they missed the written answers, can hear the questions and answers as well. Let's see. So there was one general question, and I'll, I guess, throw this to anyone. Here we go. Okay. Adam is typing, and so it knocked it out. Everyone keeps using the phrase CV data. What CV data? Collecting all of the raw BSM data is not reasonable, but if you think about edge computing and consider speed data and at what frequency, 10 hertz BSMs from every vehicle within range or an intersection is absurd. Ben answered in the pod. I don't know if you want to, Ben, if you want to answer, reiterate what you wrote.
Sure. Sure. I hope my microphone's working this time pretty well. So the edge computing, maybe the people on the webinar do not know, but edge computing is pretty much like moving the processing of the data from the big data cloud, or where the data is stored, to the edge where it is collected. And this is happening pretty much because more and more data is being collected, and faster, as Robert is pretty much referring to it right now. So a lot of things that are happening with edge computing are also happening in coordination with machine learning, and especially with deep learning. And as the devices at the end of, at the edge where the data is being collected, like the road sensors, may not have the compute capabilities, very, very computation on the data that's coming in. So to develop them, you still need to have some kind of data at this point. Eventually it will reduce, but at this point you still have to have something. So yes, there's a question in trying to figure out what do you need to store out of that flow of data in order to efficiently develop edge computing devices. But that's kind of like the next step of the data, which is now that you have started to collect the data, you pretty much have to, and that your amount of data is increasing in speed and volume even more than you had before. How do you push the analysis to the edge, to where the data, so you don't have as much coming in and more actionable information? So hopefully that answers it, but I'll be happy to add on.
This is the PA Turnpike. We just started a connected corridor. I think it goes from Harrisburg to Carlisle, with the edge computing, with the connected vehicle. That's going to probably roll out here in the summer. We're looking at a lot of those things: security, what the messages are, how much the messages are coming in, can we store the messages?
Security.
Yeah, the security thing is a huge thing because it's maybe personal information on pieces of that. So we're just starting this connected corridor. We think it's a great project, but the same questions you have, probably the same questions we have.
Yeah.
You know, what range is the roadside unit good enough? How many do we have to have? You know, industry can spec out, hey, you need you know, one every 150 feet, but we really don't know that with the sight distance, how fast vehicles are going, multiple lanes. There's a lot of different questions that need to be answered that we're trying to do with this pilot project that I think is going to open up a lot of, you know, eyes here, and, you know, and in the transportation industry. So I want to kind of add that to that question.
This is Chris. I'd kind of like to jump in as well. When we're talking about DSRC, if everybody can hear me, when we're talking about DSRC and things, I understand the idea that we don't need to process all this data, et cetera. And to some degree, I agree with that almost. Our issue really comes down to vendor lock-in. I won't mention the vendor and I won't mention the issue, but we've had an issue over the last couple of years where we're producing data with some devices, and the vendor, since we rely on them to receive the data feed and receive the understanding of that, we're kind of held hostage. And we made it very clear to our DSRC vendors that we're not going to get locked into a specific vendor anymore. We are going to understand that data. We're going to understand the records coming off of that hardware. We're going to understand how to do it. We still may end up paying them for a consolidated data feed or even a dashboard or something. We may still pay for that, but we want to have that understanding for ourselves so that we know and can compare what we're seeing with what they're showing us. The vendor that we're locked into right now, that's a serious problem. They're showing us one thing, but their data feed, once we process it, shows something very different. So now we don't really trust that vendor's output. So that's another reason for us. It's really just a matter of trust or distrust. So we are going to scale so that we can process DSRC data ourselves. That may not be reasonable, but we've been bitten by this before, so we're going to at least try to do that. And we may not continue that by the time we get to 2,500 signals. That may be, like you said, it's ridiculous. So we may not do that, but we're definitely going to start in that direction. So that's kind of how that came about.
Okay. Great. Thanks, all. So I guess we'll start up the top some questions for Kentucky. Are you hosting the whole system yourself or hosting using cloud service?
We're forbidden from using cloud services, or we were when this started. Our centralized IT department has just started allowing Kentucky state agencies to use the cloud, but only through them. So we actually have an on-premise system. I think we're up to maybe 25 nodes now or something on our cluster. And so overall, so we're all on-premise right now. And those are physical machines. Those are not VMs.
Okay. Let's see, and there was a question about some sort of a time warp. You're getting relevant data before an incident happens, and I know you kind of cleared that up, Chris, if you want to clear up the question about the incidents, identifying the incident.
Yeah, I'm sorry. Yeah, that was actually, that lady, that was a secondary crash. That was a fatality in the queue. And my point there was that we detected the first crash and the first kind of point of congestion 2 hours prior to that. And what I'm trying to do with our system is push out information to help mitigate further congestion and help reduce crashes and in turn hopefully reduce those fatalities. So I just thought it was very sad that we had data 2 hours prior and this lady ended up dying in that queue. But just an example of how data comes in and you're sitting there looking at data and then you get a news report of that happening. So it was just kind of rattling for me. So I keep that slide in my presentations just to ground things a little bit.
Okay, thank you. The next question, from when you were speaking, you talked about organizing your data and how much more usable it is after that effort. Is that correct? What are some of the steps what are some of the steps of the organizational effort? Did you already show a slide about this?
Yeah, it became very easy. Most people, they didn't want to try to understand probe data. When you tell somebody that something happened at GPS location, X, Y, and certain timestamp, that really doesn't make any sense to them. And even some of the street names and things that you get in from the other vendors, whether it's here or Waze, maybe that doesn't match what you're typically used to seeing. Our people typically use route numbers or road IDs and things, and whereas the vendors typically give you like a street name. So it made it a little more difficult, and sometimes those don't match up. So if you're taking here data and Waze data, and you want to see what happened on US 60 or something, sometimes those don't match up. So what we did was we took kind of everybody's common understanding, which is our linear referencing system, which everybody uses the same terminology. It's RT unique, district, county, route, mile point, beginning mile point, ending mile point for line segments, etc. So we gave everybody, we processed this using common language for everybody in the cabinet so that engineering staff or even non-engineering staff like policymakers could look at this and say, okay, we understand that this happened on this route or whatever. They don't have to kind of translate from what a crowdsourcing says the road name is versus what the route number is. So we try to put it in their language so they can understand it. And I think it's helped with our adoption rate because now people can just open up Elastic and say, oh, I don't really understand the tool, but I do understand the data. So this happened at this time, and we even do 2-minute increments on our timestamping. So we round to 2 minutes because what I told our developers was I should be able to pick any, on our 27,000 miles of roadway, I want to be able to pick any district, county, route, and mile point in any 2-minute period and find data. So that's what we did. So not only do we record the capture time of the data, like Waze, for example, they give a refresh time on their overall data feed. So we capture that time, and then they also give us a publication time of when something first was published to their data feed. Well, if that record persists for 30 minutes, that may have been 29 minutes prior to when you grabbed the data. So we grab that timestamp, we're grabbing the feed timestamp, we grab our capture timestamp, and then we also do a time of existence to 2 minutes. So in other words, the existence time is when did that record actually exist on the roadway. And we process that, we round it to 2 minutes so that everybody can use that 2-minute timestamp and understand, oh, if I'm looking at this 2-minute timestamp, regardless of what the other timestamps say, this 2-minute timestamp means that this actually occurred. This was the current condition in existence during this 2-minute time frame. So it made it very easy because then people, they're already going to have a learning curve with the tool. We did not want them to have another learning curve with the data. So it was easier to say, hey, we've got some really advanced tools, so we need to simplify the data. And so we put that burden on ourselves instead of training both ways. We just made the data easy to read and then turned them loose with the tool. It made it easier for them to understand the tools.
Okay. Thank you. Let's see. The next question, relative to INRIX or Waze, et cetera, et cetera. Was your slide showing that they were faster or more accurate, or that they differed in what they were indicating? I guess we can start with you, and then maybe if Turnpike has any response to this, they can chime in as well.
That's correct. We're seeing the probe data and the crowdsourcing data come in long before we get calls. And Genesis Pulse is actually a great example of this. They integrate crowdsourcing or Waze data into CAD systems and dispatch systems, and they actually, based on all their customer base, I think they've got 1,200 customers, they're seeing a 4.5 minute lapse in between the time they get a report in from Waze and probe data versus the 911 call. And it's I forget what they call it, there's a term for it, but typically people pass by and they think, oh, someone else probably already called, so then they don't call. And it actually, there's a lapse there. People are, there's an average of 4.5 minutes. For us, it's much greater. We have a legacy workflow where someone from the roadway, someone out on the road, calls a district office. The district office will write something up and send it to our traffic management center. Then our traffic management center re-enters that information. So it actually goes through two people, and that process has proven itself to be inefficient based on probe and crowdsourcing data. And that's what we're seeing now.
Okay. Pennsylvania, do you want to respond to anything related to timeliness of different kinds of data that you receive?
Yeah, and again, I'm going to go with probably what Chris just said. When we get our probe data and when we display our probe data and when we're looking at our probe data, it's relatively accurate, but also there's a level of probe data there for the Interex data on whether it's actually real time or not. So level 30 for us is real time information, but out in rural, PA, we may not be getting all of the probe data real time and right away, so they go to a historical value. We've looked and asked Interex to say, out of those segments, give us a percentage of when all those segments are at level 30 and we are getting real-time data, because it does affect how you look at that data and if that data is real when you're looking at it. So that explanation and, that thing of looking at level 30 and how much level 30 we're getting in and how good that data is, again, is something we need to look at. The Waze stuff is a little more interesting, like I said in my presentation. Location of when that person hits that button, or a passenger may hit the button, or, hey, he's just stuck in the backlog and reporting an accident. There's a lot of different things you can do with that information. Again, it is coming in sooner. We've been out there, and I will tell you, every Monday and Tuesday, I sit here and I get Waze alerts that are for accidents, and I walk right to my TOC, and I'm like, there's an accident at 3:35, and I am not kidding you. 3 or 5 minutes later, there's a call. There's an accident at 3:35, and it's not the best data in the world. It's not the best QA in the world, but I've been doing it for probably about 1.5 years now, and it's pretty, especially down in the urban areas. As soon as they click on that, boom, it's done. I walk in and say, there's going to be an accident here, and by God, it's somebody's calling saying, hey, I have an accident at 3:35 with injuries. And, so like I think our duty officers and our operators are starting to look at Waze more. They're starting to look at their section of roadway and seeing how busy it is and seeing if a lot of that correlation is happening. But, that's real-time, real-life stuff that we're noticing on those particular data sets that are coming in.
One thing you have to keep in mind, though, is also the current conditions when you're looking at that data. We just saw an anomaly during our last winter storm where the Interex data seemed to indicate accidents a lot sooner than Waze, whereas typically it's always been Waze. And we started realizing, well, with the winter snow and everything, people are already going 45 miles per hour on a 70 mile per hour roadway, so not because of an accident, just because of the weather. So, just keep in mind of everything that's going on when you're looking at that data.
Oh, yeah. The weather has a lot to do with it.
Yeah, this is Ben. I wanted to add something about the waste data. I had the chance to analyze 5 years of data nationwide, and it is interesting to notice that people report very different areas. The quality may vary a lot when you look and where you look. So this is a typical.
Okay. Well, unfortunately,
Can I add one more thing to a question that just popped up from Michael about level 30. Level 30 is part of the data feed that we get from INRIX. It tells you if it's a level 10, 20, or 30, and it basically says whether 10 I believe is historical, level 20 is average or some type of mix, and level 30 means it's actual probe data. So it's just part of the feed when we say level 30.
okay, great. Thank you for clarifying. Unfortunately, that wraps up our time for today, and I appreciate everybody's great questions. And I guess they'll probably be Adam. Will the questions be available with the recording?
Yes, definitely. All these questions will be available on the recording. It was a great conversation.
Great. Well, I want to just thank everyone who took time out of their busy schedules to be with us today, and also give a special thank you to all of our presenters. I want to make a quick note that the final documents for the NCHRP 1775 are not yet available, but they will hopefully be posted soon, and when they have been published by TRB, I think the National Operations Center will send a link to the webinar participants that the documents are available. So, as we've mentioned, the recording of today's webinar will be available soon for anyone who wants to listen. And so I just want to wish everyone a nice day and good luck with your future uses of TIM and big data. Thank you all very much.
Thank you.